Dear students, let us discuss in this video lecture on how convolution neural networks are able to perform very efficient classification and feature extraction. Let us get few of the insights and understanding on what kind of features does they extract and what kind of attribute we can associate to them for doing efficient classification. So we have so far discussed on different kind of classifiers, especially CNN based classifiers, different CNN architectures that are applied for classification in ImageNet on ImageNet dataset. As we discussed in the previous video lectures, the convolution neural networks based feature extraction and classification is the best among the developed classifiers so far, and they outperform the classification by many folds compared to computer vision classifiers. So let us see what kind of features typical convolution networks or Conv-Nets extract, and try to visualize few of them or try to understand the efficiency of the feature extraction in some of the cases. Assume that we provide an image and we are doing classification through a big convolution neural network, and we have a large data to train it, and we are doing now 1000 classification as we were doing in ImageNet data set, and we start understanding this convolution neural network through visualization at different levels of the feature extraction. So typically we divide this into three levels. One is the features that are extracted at the first layer, and feature extracted at the last layer, and the feature extracted at the intermediate layers. I would like to acknowledge that all the slides I am using in this video lecture are from Professor Fifi Lee team, and they are taken from the CS 231N course by Stanford, and few of the lectures are taken from respective publications where they were cited. So let us understand how the visualization of the features or the kernels at the initial layers look like. Please note that the kernel at the initial layer is like performing the correlation with respect to the input image and giving some features. So typically the kernels at the input where they are correlated with the image can be considered as the pattern of the kernel can be considered as the pattern that we are extracting the subsequent layers. So if we visualize the kernels, they look like that. Say for example, in different nets like LXNet, ranging from LXNet, DresNet and DenseNet, the kernels in the first layer are visualized like here, and they look more like edge-based features. So you can see that what we are visualizing here is if we have 11 cross 11 kernel, and it is taking from 3 maps to 64 maps in the first layer, we are visualizing 11 cross 11 cross 3 here in one of the images, and there are such 64 here. Please note that each is a color image that we are visualizing here. So it is 11 cross 11 cross 3, and there are 64 such sets of images or or the blocks or the filters we are visualizing here. Please note that each of these is one filter, and that filter is extracting the information of from extracting the information which looks exactly like the filter in the input image to the next level. That means it is highlighting the information that looks exactly like the filter. It's like if you want to find edges, we convolve with an edge filter, and if you want to find uniform regions, we can convolve with a averaging filter, and so on. Okay, so given that intuition, what we are doing is we are convolving these filters implies that these are the filters which are these are the patterns we are extracting in the subsequent layers from the at the first layer, especially at the first layer. And these filters now are not preset, and these are learned. So through learning for feature extraction and classification in different frameworks, we can notice that uh, mm, what is happening through learning is the filters at the first layer are more like more extracting edge based features, and which also agrees with some of the neuroscience findings that even the visual system extracts edge like features at the primitive layers. And now if we visualize in the similar manner the kernels or the filters at the subsequent layers or at intermediate layers, so they doesn't they look like this, but they doesn't give very good intuition on the kind of features they extract or on the kind of any typical pattern that they may have. The reason is the input is an image which is in pixel space, so we can clearly identify what kind of features we are extracting. And once we convert to feature map, then we only have conversion from we extracting high level features from low level features, and thus these kernels doesn't really make great sense. However, the at intermediate layers, what we can see or we can understand what the process of feature extraction or learning in CNNs is through activation maps or the feature maps itself. So once we convolve with the features at the intermediate, once we convolve with the filters at the intermediate layers, what we get are the feature maps, and these feature maps can be seen to identify some of the prominent locations of the input image. So for example, if when we consider some of Conv layer in one of the deep network, we can see that it is extracting where the human face is high, located. So it gives high response. The activation maps is giving high response to the location of the human face. You can refer to the understanding neural networks through deep visualization paper for more details on this. So now further intuition on this can also be gained by looking at the activation outputs for different input samples at a given layer. So these activation outputs from may keep changing with respect to the input sample, but the if we identify it in any given layer, say for example, say in some Conv layer here and a particular channel, 17th channel here, if we identify the outputs for different input images, we can see that few of the neurons fire maximum at most of the for most of the images or a particular class of images. And those neurons, if we see the receptive field of the neurons, for example, as you know, each of the neuron has a receptive field in the input, and the receptive field of the neuron at the deeper layers will be even higher. So as we discussed in VZZ framework, when we go with 3x3 filters over 3 layers, the receptive field of the neuron at the third layer is 7x7. Though each neuron looks at only 3x3 lesion in the next immediate layer or the previous immediate layer, its receptive field in the input image space will be 7x7 or even higher based on the depth of the layer and the extent of the filters in each of the intermediate layers. So now if we take an output neuron and see the input patch through the that is spanning the receptive field, we can see that they keep extracting a similar kind of patches. For example, if in some layer and some channel, if I keep identifying the neuron which is firing maximum or whose activation function is maximum over a reasonably large for large number of images, then that if I see the receptive field patches corresponding to the receptive field of that neuron, they may look like this. So that neuron is all identifying similar kind of patches. Similarly, in another layer or another map where I get the maximum activation, the patch may be like this. So each patch is extracted, like each neuron which is firing maximum in any particular layer and particular map is identifying some kind of is firing for some kind of pattern in the input image. So and this gives some kind of intuition on what kind of features does these intermediate layers are extracting. This can be identified based on the patch that each of the neuron is looking at in the input image, or the receptive field for which it is giving the highest activation in a particular layer, or it can be seen in the feature map where it is very the values are high. Value being high in feature map indicates that the region is more focused. That region is being highlighted for the classification or for any other computer vision application through learning in that convolution neural network. Now let us understand what are the features that are extracted at the final layer. So imply, or how do we understand that we are learning better features in the final layer in a deep convolution neural network. So this is again explained with LXNet framework. Assume that we have 4096 dimensional feature just before the 10 cross like 1000 cross 1 or 10 cross 1 output layer in the LXNet. Now these pre-final layer to the output are referred to as the features that are obtained from the network, and these features usually can be also be used for classification with using any other conventional classifiers. So if we extract features through convolution neural network and use these 4096 features, that is the features just pre-final layer, those features can also be used through SVM or Bayesian classification and any other framework for classification. That means we keep giving the input samples of different categories, extracting those features, and once we extract all these features, we can these are like conventional feature extraction we have been doing in two-stage framework for classification, where feature extraction does first and then classification. And these features, 4096 features through convolution neural network referred to as deep features, can be given to any other classifiers for better classification. And now we will try to see what these features are extracting. So to see what these features are extracting, one of the experiment done by some of the researchers given here is that they we see the relevance of these features compared to the nearest neighbor classifier we apply in pixel space. For example, if we have CFAR dataset where we have actually different image classes, and we try to find for each of the test sample, we want to identify the better label through training data, and we apply nearest neighbor classifier. Say for example 5 nearest neighbor classifier or 6 nearest neighbor classifier here. So we extract some nearest neighbors, 5 nearest neighbors here. Assume that among these 5 nearest neighbors, which is the more frequent class, is the class that we assign to the that label we assign to the input image. You can see that the 5 nearest neighbors here are different. They are not exactly corresponding to the same class. Here, for example, for aeroplanes, we got the horse as well as one of the nearest neighbor. And for frog, we are getting some other cat as well as one of the nearest neighbor. So the nearest neighbor in pixel space are not all corresponding to the same class. Whereas if we now use, say, assume that this image is given to Conv-Net and we got the features, and each of these training images are also given to the Conv-Net and we got the features. Now what we try to, we assume that we have the features of test image and compare the features of test image with all the features of the all training images, and we identify the closest images are the nearest neighbors in feature space now rather than in the pixel space. So through conv features or through deep features, and the identified images through features or nearest neighbors are these. You can see that all the nearest neighbors are of the same class. So it implies that the features that we are extracting are very efficient, and they are invariant to image pixel variations, intensity variations, shifts, or even view variations, or they are very robust to cluster together for the same category. That means these 4096 features, if we cluster in 4096 dimensions for all the training images and test images, we can see that all flowers category will have their features at one location, one small subspace of 4096 dimension. Similarly, all elephant images will have another subspace, and so on. Okay. So to verify whether this clustering or the grouping is happening very well or not with these features, or to say whether these features are very efficient or not, the way to look at is to project them onto two dimensions where we can easily visualize and look where the features are. One way to do two-dimensional representation of these 4096 features is through PCA, which you know, principal component analysis. We can project them to eigenvectors of the covariance matrix of 4096 dimensional features, which is 4096 cross 4096 dimension covariance matrix, and we can identify the first two prominent eigen directions through corresponding to the highest eigenvalue of this matrix, and then those principal eigenvectors can be considered as the directions to project the data, and then we can project all 4096 features onto the dimension, and we can see the principal components after projection, or the dimension reduced features of each of the training samples or test samples. And then if we now plot in two-dimensional space these features, two dimensions projected features, all cats may be in one location in two-dimensional space, all dogs may be in another location, all persons may be in another location, and so on. And now very good clustering in two dimensions indicates that the features in 4096 dimensions are very efficient. But while reducing from 4096 dimensions to two dimensions, the bottleneck is that we are reducing the dimensions by very vast reduction, and hence it may not really capture whole information. So efficient dimensional reductions are required, and TSNE is one of the very good way of embedding the information into lower dimensions. So you can refer to the corresponding paper for more details on how exactly this TSNE embedding works. But through TSNE embedding, if we now bring these 4096 dimensions to two dimensions, we can see that they all cluster very well. That features extracted from deep networks are very efficient in bringing the same class samples together, and different class samples different. In fact, based on this understanding and observation, and to enforce better and better clustering of say intra-class samples together and inter-class samples far away, there are different cost functions that are developed in CNNs, and they are like triplet cost function and contrast loss function, etc. So now let us see how they work. Such embeddings work even for large data. If you previously what we have shown in two dimensions are the data points, but now in this two-dimensional space, at that data point, let us put the small image in very small dimension, or put the image representation, so that actually we can see whether all the images are clustered very well or not. And you can see here most of the green small plants are here, and then small TVs probably are here, and different objects are here, persons are here, and so on. So this you can see in higher dimension like this link by Stanford, where you can notice that the clustering through CNN features is way above the usual feature extraction methods. And the other way of understanding what this network is doing, the land network is doing, is to get a heat map or density map. based on the land network. Assume that we have trained a deep network, and now I want to identify the importance of each of the input patch of a given image in the output. If the, say for example, if the image is with say go-karts, then wherever is go-kart is there, ideally I would like to say that the network gives more importance to that, and wherever there is no go-kart and where is there is a uniform regions or background, the network should ignore or doesn't pay more attention to this. It's like an attention map on the image for the paid by the network. And for the elephant, say in the face region we should give more importance, and in the other regions we may not care much. Now this, what we do is to observe that from let us take a original image like elephant image here, and place the mask at different locations, and once we keep changing the location of the mask, we try to get the probability change in the probability. That means, say for example, if the output probability for the elephant class, if I keep looking at for each of the locations here and plot in 2 dimensions, at this location the output probability is changed. Say at this location the output probability changed from previously probably the change in probability is the probability has reduced a lot, so it's now 0.4 or very small. So previously assume that there is 1 there, so now it's 0.4. So it means that the output probability is very affected by masking this region. So the effect is more wherever the red regions are there the probability after masking is less, or the probability drop is more, or the effect of mask is high. So this most affected region is in red through the mask, and hence these locations are more important for deciding the object class. Similarly, for the go-kart, you can see that where there are some go-karts, you can see high probabilities changes in high drop in probability, and similarly for the class label, for the corresponding class label, similarly for the other image. So you can refer to this paper on visualization and understanding of convolutional networks for better details. This is another way of understanding CNNs, or provide from the land network, observing a heat map to see which are the regions that network is more looking at to take its decision or classification. Thank you.